I am happy as always to be part of any activity of this college. It's needless to say, I suppose, because I was an old student of this college. I grew here in more ways than one. So when I was asked to speak on something that would interest a general audience, I was kept thinking as to what it could be, because rigorous mathematics might really put away many people. And if it is not maths, then well, I cannot be writing in my first slide that I am a professor of mathematics. So there was a dilemma. So I had to really decide what to say and how much to say. And to kindle interest in an area which has become quite important in the recent past, I thought let me speak about Edward Lorenz, the mathematician and meteorologist, talk to you about the person, talk to you about the maths the reason why I titled it as Unknowingly Created with UN within brackets is we are not sure whether he really knew what he did and whether he was aware of previous work in that area. Okay, so there is no literature which talks about his prior knowledge of that particular area, which came out of his work in meteorology. So that is the reason why I decided to have the title of the talk in that particular way. Edward Lorenz taught at MIT, Massachusetts Institute of Technology. He was endowed with excellent skills in mathematics. He was very passionate about mathematics, in fact. His physics background was excellent. So that made him a good engineer as well. With the two backgrounds that he had, that made him a good engineer as well. What endeared him most for fellow researchers was his excellent behavior, the way he treated people. I'll not say more on his life. I'll speak a little about his works. I'll speak a little about the implications of what he did. Dr. Edward Lorenz was liked so much by his students and friends that all his PhD students, their family, their children, the grandchildren were in contact with Dr. Edward Lorenz. This is no exaggeration. He was in contact with each one of them, his students, their families, the children, their grandchildren as well. And one most amazing thing about the individual was he knew the names of all his grandchildren. Okay. Normally what happens if one is past some age, the grandchildren deliberately come and stand in front of you and ask what is, grandfather tell me what is my name, or grandmother tell me what my name is. So this sort of thing happens. Even at the age of 91 when he died, he remembered everyone's name. Not to forget all his friends, even their families as well. So he had an amazing memory for names. He had an amazing memory even for birthdays, mind you. He remembered the birthdays of many of his friends and that is his children and many others. So that was Dr. Edward Lorenz for you, a human being. Perhaps because of this very endearing personality that he was able to attract many people. See, it is not just that because someone is very good in the subject, you get attracted to him or her and do good work. According to me, if someone comes to you It is first because of the comfort level which the student has. The second thing that appeals, that is my understanding from my experience of 30 years, the second thing that comes to the student's mind is how much of a scholar the teacher is. So then when someone joins for a PhD program, I think these two considerations are definitely there. So there was everything in Edward Lorenz. So perhaps there was a lot of competition to just join him for a PhD program or do a project with him. I just imagine this. Because I was at the National College, I cannot forget the two. Okay, I was influenced by both. Yes, now to Lorenz again. Edward Lorenz came up with a seminal paper. It was titled Deterministic Non-Periodic Flow. This particular paper, which appeared in '63, no doubt became famous, but it did not become famous immediately. It became famous a little later, almost a decade later, 9 years in fact to be precise. It was in '72 that that paper really saw the light of the day in terms of recognition. Edward Lorenz was actually mainly a meteorologist at MIT, though he was known to be a good mathematician. So he was doing a lot of work on climate dynamics, especially in numerical weather prediction. That was the time when the world's first electronic, you know about ENIAC, the world's first computer. So that was also invented around the time, and that was the time he was able to lay hands on some of these machines. Most of the calculations that he did thus far, till that particular time, was hand calculations, mind you. They did maybe with small time calculators. So during the time when this invention happened, he was able to use that machine for climate modeling, especially numerical weather prediction. Edward Lorenz, at the back of his mind, always had a feeling that long-time prediction of weather, climate, was perhaps not correct. He had that feeling. We all know this. When the weatherman predicts something for us, we are skeptical when it is of 1 week. If the prediction is of 1 or 2 days or a few hours, perhaps we believe that, because the prediction, the acceptance of the prediction has been good only when we have seen that that is really happening. So you take the case of tsunami, for example. The warning was just a few hours earlier. So let me go back to this. So he was trying to do something on that, on numerical weather prediction. He was always thinking at the back of his mind that numerical weather prediction might not be really correct. Long range predictability is incorrect. So he had that thing in mind whenever he did something on that. So with that feeling, he started making use of the equations which govern climate dynamics. He started making use of the equations. Then, since he always believed that short time behavior can be correct, he thought, if short time behavior can be correct, why have the full model? Let me take a simplified model of the full one. So that is what he precisely did. So he took the full equations, simplified them, without compromising much When I say without compromising much, what do I mean? Without compromising the essence of what we see in the case of climate dynamics. So that is what he did. So he was making use of Fourier series expansion in his work. So he used a few modes. In fact, the most minimal mode. The most minimal mode that should have all the characteristics of atmospheric dynamics. So he picked up 3 modes. That is the most minimal mode one can have in the case of climate dynamics. So he picked up 3 modes. He built up a model using Fourier series, as I said, just with 3 modes. Then started running the computer program to find the numerical solution. That is how it started, because he had this computer with him now. So he started finding out the solution. When he started seeing the solution, see, it is not like today. Suppose I have the same Lorenz equations. Within 5 minutes I can compute the solution and even possibly show you the trajectories. Okay, real time. I can do that. But that was the time when they had to write a program, punch it in cards, okay, submit it to the machine, then it is called as batch processing. That's what they basically did during that time. So with a lot of effort, they got some results. So he was seeing the results that he obtained. He thought that he had done some mistake. He did the programming himself. He then thought, he repeated the numerical experiment several times. He still got the same result. He gave it to a student thinking, when one sees something repeatedly, one does not find out the mistake. So he gave it to the student. The student got the same answer again. So then he thought, there must be something in this. So he started analyzing the result. So what he observed was short time. His interest was short time behavior. What he observed was the solution. I will shortly show you the nature of the solution. The solution of the equations that he obtained, the trajectory, if you plot the graph of the solution, they were all bounded. They were all doing they were taking the form of a butterfly within a finite volume. Say a finite box or a finite ellipsoid or whatever it is. We will not worry about that. Within a finite volume, the solution curve kept on going like that, in the form of a nice butterfly. That is what he called it, the butterfly effect. He was curious. Why is it that it is happening like this? I have a solution curve, it's non-linear, the equations are non-linear, I found out the solution, it's going around and within a finite volume. Then what he did was, he started experimenting. Since he was confident that what he had done was right, he started experimenting. He changed the initial conditions. Okay, don't worry too much. Non-mathematics people need not worry. So, to start with, we have certain values to be given. So, he changed those values. What he observed was, to his utter surprise, when the conditions were changed, the nature of the solution remained as it is. But it took a slightly different path. So then he realized one very important thing about the equations that he had now. What was that? The equations are very sensitive to the choice of initial values. Sensitive dependence on initial conditions, it is technically called. So once he saw that, he began a series of experiments because he was amazed at what he got. He talked to friends about it, that this is what he is getting. Many of them would not believe, as happens to many scientists. Even when Chandrasekhar announced something, what he did, many people did not agree. It happened to Lorenz as well. When he talked about such a differential equation, they would not believe that. He talked about deterministic chaos. If something is chaotic, how can it be deterministic? And under what conditions is it deterministic? So several such questions arose. So he started writing about it. He did not write much in this paper, mind you. His focus was mainly on climate dynamics, especially numerical weather prediction. So I will just talk about these things. So that is the abstract of his paper in 1963. Number of books deal with this now. Okay. Edward Lorenz, as the literature goes, was not aware of many similar things which were there, like the differential equation that he came out with. There were many things. These things you can see in celestial mechanics. So the positioning of the stars, for example, if there is a slight change in the initial conditions, the trajectory can be something different. Similarly, oscillators. Since it is a social science forum, I thought let me bring in some economics as well. And Lorenz's work is relevant in the present day. It is relevant in financial markets. It is relevant in stock markets. A lot of such models are being used for various things. I'll not dwell on that because that is not the point of my talk. Many people, Maxwell put his hand on these things. It was a touch and go type of thing. Maxwell did some work. Hadamard did some work. Poincare also did some work in this area. Cantor, during the time of Cantor, there was a talk about fractality. Okay, so he also put his hands in this. It was Anaxagoras who first made some real attempt to do something on the type of thing which Lorenz did, but though not on numerical weather prediction. Then Cayley called it erratic dynamics. Okay, so there was a feeling that whatever these mathematicians or physicists were doing, they are basically outcomes of certain mathematical recreations. Okay, these people are trying to spend time. That was the feeling. Many non-mathematicians felt like that. So, in spite of such a feeling among non-mathematicians, these brave mathematicians carried forward. Okay, but they were not known until, mind you, they were not well known. They did not become well known until Edward Lorenz came up with this work. If you really want to have a nice book on chaos theory, there is a book by James Gleek which came out in 1987. It's a good book even now. It's a book of 1987. It is a good book even now. I'm emphasizing that. Okay, it's for general reading. You can really enjoy that book. Now we know that during the last century there are three very important things which have happened. One is relativity, the other is quantum mechanics, and the next thing to happen is chaos theory. So many of these things, Lorenz had a predecessor in Salzman who had similar ideas. Lorenz was aware of the work of Salzman in MIT, and there is documentation of Salzman's work as well. But that is, the motivation for Lorenz's work might perhaps have come from the work of Salzman as well. So that is one of the things which Edward Lorenz himself says. So what is the motivation for the Lorenz model? So if you see the Lorenz model from the physics point of view, you will have unexpected instabilities. I am talking about not the classical Lorenz model. Lorenz models which have evolved of late. You have generalized Lorenz model. So there is a possibility of certain other types of motion, unexpected instability. If you ask a mathematician, he would talk about nice differential equations and Fourier analysis and all that. If you come to aesthetic aspects, the solution that it generates, it shows nice patterns. I will show them very soon. So what basically Lorenz did was, you all know that the surface of the earth is hotter than the upper levels of the atmosphere. So due to this temperature contrast between the surface of the earth and the upper levels of the atmosphere, the air circulates, the global circulation, the wind, everything, they happen because of that. Differential heating of the atmosphere. So the air near the surface of the earth, it gets heated up, it becomes lighter, so it moves up. How far can it move up? It moves up that much as the energy that it has. So it rotates in the form of nice circulating cells. There are three different cells. Okay, I don't want to go into that, how the atmospheric circulation happens. There are three cells, one in the near the equator, one in the mid-latitudes, the other in the polar region. Basically, the horizontal component of those circulating cells are what we call as winds. So now, what Edward Lorenz did was try to model that. This experiment was done already, okay? But when does this circulation happen? Okay, after how much of heating does this circulating pattern happen? That was the investigation which was reported before Lorenz. Lorenz did a study which was more general in the sense it was non-linear. Okay, whatever that means. So, basically one gets a Lorenz type of flow or the atmospheric circulation type of thing. If you consider, for example, two horizontal plates, you have liquid in between, you heat the lower plate. What happens to the liquid very close to the lower plate? It gains energy. Okay? When the temperature, when you keep on heating, it overcomes viscosity, it overcomes thermal conductivity. So, when it overcomes all those things, then it moves up. Because lighter things move up, heavier things come down because of gravity. Okay, buoyancy what you call it. So, this is a typical Rayleigh-Benard experiment which Lorenz considered. Now these sort of patterns which you have, you can see in circular containers or square or any of these fancy containers. This experiment was done by Koshmidar, who took a circular container, he heated the liquid, okay, and he took silicone oil, I think it's written, yes, silicone oil, he heated that and saw these nice patterns. Koshmidar also did an experiment with these containers. Okay, so a number of things were seen. What Taylor did, let us see. What Taylor did was, he took a solid cylinder with an outer concentric hollow cylinder with liquid in between. So you have an annular, you have a solid cylinder. Outside what do you have? You have a hollow cylinder, solid cylinder with an outer hollow cylinder, liquid in between. Taylor differentially rotated the cylinders. So when he differentially rotated the cylinders, to his utter surprise again, what he saw was something similar to what Benard saw in his experiments. What did Benard see? So you see here, this is anti-clockwise, this is clockwise. So this is the solid inner cylinder, this is the outer cylinder, the boundary of that. You have liquid here. When he differentially rotated the cylinders, what he observed was counter rotating cells. This was precisely what Benard observed in his experiment. This is what precisely Lorenz considered in his experiment, but different aspect. Okay, so that is what you see. So you see in the Bernard experiment, you see counter rotating. This is clockwise, that is anti-clockwise. Okay? So this is anti-clockwise, that is. So you have counter rotating cells. Fluids always take the path of least friction. Suppose both the circulating patterns take, say, a clockwise circulation, what happens? Okay, when they circulate like that, there will be friction, there will be maximum friction. When they counter rotate, when it goes up here and comes down, they come together, there will be least friction. Fluids always take the path of least friction, that is what is observed. So you can see this nice hexagonal patterns. Okay, Koshmider again did this experiment. Number of fancy shapes. You can see such patterns, really Bernard-like patterns, in the clouds during some seasons, not all seasons. It was seen even in lakes, not due to temperature but because of salinity. This was seen by a satellite in the west coast of Africa. Okay, so this was seen. Now let us take another thing. I talked about two things now. What was that? One is, I talked about a horizontal plate with a liquid in between. You heat from below. You see nice patterns when you observe from the top. You take two cylinders, one solid, the other hollow. You have liquid in between. You differentially rotate the cylinders. What you observe is Bernard-like cells, counter-rotating cells. So now, this is something else. I have a box. I have liquid and its vapor inside it. It's a glass box. I want to see everything. I see from the top. So what do I do with this box now? I have liquid and vapor. I hold the box and vibrate it slowly, not violently. Okay? So once I do that, what I see is patterns like this, very similar to what I saw earlier, which Koshmider did. Okay, the really Bernard experiment. These things are happening within the Earth's mantle as well. Okay, so convection happens within the mantle, Bernard-like. Okay. This happens in geothermal reservoirs also. So this is a very important mechanism. It happens even in the stars, especially the sun, for example. The convection that happens there is in the presence of a magnetic field. Okay, it's called magnetoconvection. So they are all related to this. The supporting of the infinite dynamo, what we call. Okay, the principle is very similar to what we have here, geodynamo and things like that. I don't want to go into the details. So these are the things. If one simulates, see, when you talk about simulation, you have an equations and you solve them and you animate the results, so you get some sort of figures like this. So basically you can get these things in the laboratory, okay, numerically, using the computer. Now let me come to, this is an excellent book, even today it's an excellent book, okay, Strogatz. So these are the Lorenz equations. I fancied putting them on a jacket because I showed you the first photograph. I think he was with a jacket. Most of the times, Edward Lorenz was seen in a jacket. The reason is, he was a multifaceted personality. It was not just mathematics or meteorology that he was interested in. He was interested in hiking, mountain hiking. You will not believe, we cannot hear of such things these days perhaps. He took the weekend, he took some of his students on top of the hill and gave lectures to them. He carried the blackboard himself. Okay, he took all his students to the top of the hill and gave lectures on top of the hill. That was the type of passion that he had, and most importantly, that was the type of passion his students had. Okay, not merely the teacher, even the students must have that passion to learn from such a teacher. So I fancied putting this. So let me come to the equation now. Now these are two troublesome terms, okay, xz and xy. When you want to solve differential equations, terms like that, what we call as non-linear, are difficult to solve. Okay? In fact, this equation is impossible to solve. Okay? Impossible to solve in the sense, right?
You can't see.
The problem is, YouTube na cover makka. So munde kutundu.
ಇಲ್ಲ ಹಿಂದ್ಗಡೆ ಇರೋದು ಏನು ಕಾಣಿಸುತ್ತೆ?
Save ಮಾಡಾಗ YouTube ನಲ್ಲಿ ಬರಲ್ಲ. Like
the equations can't be seen.
Maybe.
No, I'm not talking about me. The other people.
But it's not for others. Cut out that YouTube ನಲ್ಲಿ ಬರಲ್ಲ.
And this is not solvable as well. Okay. So these equations, you cannot solve them. Okay. The sense in which I say it is not solvable is different. People say they can solve it. Okay, one person can say I can solve it. I would, as a mathematician, say it is not solvable in a very rigorous sense. Okay, so I will not go into the details because there are a lot of non-mathematical people here. So I talked about sensitive dependence on initial conditions. So this is it. Now, suppose I start with two different values. So you see, one trajectory would go like that and the other trajectory would move away. Okay? So you see they depend very critically on the initial values. People did not believe what Lorenz did because see, anything new people would not accept. It is true those times, it is true now as well. If you want to do something different, people will not agree to that immediately. Things cannot be sudden. The changes, if at all we affect anywhere, that cannot be sudden. It has to be gradually. So that is what Lorenz did. He introduced this gradually. So he had a fellow mathematician at MIT, very famous person in MIT, very distinguished mathematician. So Marcus subsequently did a lot of work with another mathematician called as Veronis. The two together did a lot of work on the type of problem which Lorenz investigated in the case of the atmosphere. So, when people did not believe these equations, when people did not believe Edward Lorenz, when people did not believe what he presented, Marcus, his good friend, decided to explain to people that this is really, in fact, a good mathematical model for something, for some critical problem. So, he came up with the concept of a water wheel. I don't have the time to go through this. It's pretty interesting. Okay, so I'll just mention this. I leave it to you. You can find it out on the net. So, this Lorenz model is a model of a physical situation, physically realistic situation, or what is called as a water wheel. So, with this work that came out in 1970 by Marcus, people started to believe. Let me not say started to believe. They started getting inclined to believe. Okay, they still did not believe in it. It was 72, 2 more years. So all this, okay, I will not go into the details of that. Here you have everything regarding the water wheel, the angular velocity and things like that, though it does not connect in the same sense with what Lorenz was doing. So this is the computer which he used. There were 113 vacuum tubes, 1450 diodes and things like that. Okay, it costed those many dollars. So, what did he do? I told you short-term predictions. He saw that they were quite nice, believable. Then he started with increasing the time. So he started seeing the solutions for a longer time. So what he observed was that long-term predictions based on such models are unfeasible. Okay. So he started out with that premise. Something at the back of mind told him that long-term predictions cannot be made in the case of the atmosphere. So he had that thought in him. With the result which he got from this particular model, he was able to say for sure that long-term predictions are in fact not possible. Okay, so we see that even to this day. So this is what you have. Lot of mathematics came out of it. Lot of mathematics came out of it. He came out with the model, but lot of mathematics came out of it subsequently. The main problem was the numerical difficulty. So I'll just show you a few things regarding this a little later and talk about it. Now in the 60s, the hyperbolic theory of dynamical system by Smale and his co-workers, that came up. That was not connected to the Lorenz's work earlier. Subsequently, they connected even that. Though the Lorenz model is not hyper, don't worry about that. Okay, we will not worry about technical things. But let me try to impress upon you that something like hyperbolic theory of dynamical systems became popular because of Lorenz's work. There were geometric Lorenz models. There were a lot of people all over the world, especially Russians. Many of the works of Russians in this particular area did not get noticed for a very long time. For obvious reasons, even to this day, there may be many things the Russians have done. We come to know about that much later. Okay, because of less communication or no communication perhaps.
ಫುಲ್ ಆಗಿ ಯೂಟ್ಯೂಬ್ ಏನೂ ಬರೋದಿಲ್ಲ ಕವರೇ ಮನೆ ಟ್ರೈ ಮಾಡಿದ್ರು ಆಫ್ ಮಾಡಿ ಸಮಾಧಾನ ಅಲ್ಲ ಇದು ಅನುಕೂಲ ಆಯ್ತು ಕೇಳಿ ಅವ್ರಿಗೆ ಅಲ್ಲ ಲೈಟ್ ಆಫ್ ಮಾಡಿದ ಅನುಕೂಲ ಆಗಿದೆ ಓಕೆ ಇಲ್ಲಿ ಬಿಡಿ ಇನ್ನೇನು ಮಾಡಕ್ಕಾಗಲ್ಲ ಲೈಟ್ ಆಫ್ ಮಾಡಿದಾಗಿದೆ.
Fine. Okay. So, Tucker, a mathematician, came up with a rigorous proof for the existence of an attractor. Now, what is an attractor? I'll talk about all these things very soon. Okay, many of these things, which I can definitely avoid for the crowd here. A lot of computation can be done. You can just see these pictures. Yes. So it does that. Okay. It just goes around those 2 points. Okay, this point in the center, this point in the center, it just goes around that. So it's that is what is observed. You see it from any angle. You see something like a butterfly. Okay, that's what he said. So now to certain other things. I will not say more than this. Now let us take, for example, this is sea, this is land. Okay? To take a simple example of how these things happen. Now what do you see over here? During the day, when there is sunshine, which one gets heated up fast? The land or sea?
Land.
The land gets heated up fast. Okay? Sea takes comparatively less heat. But the retention of heat is better in the sea than in the case of the land. Okay? So what happens in the morning, let us see. Let's say afternoon. Because the land is hotter, the air moves up here and it comes down. Okay? So you have air coming from the sea to the land. So that is what is called as a sea breeze. In the night what happens? This is hotter, this is cold. So you see that it moves up here, falls down, so then moves away. Okay? So you see the temperature contrast, they lead to some convective currents like this. They are all very, they are all connected in a way. Water wheel that I talked about, Malthus's water wheel, with the example which he gave. They actually created that wheel in an exhibition. This was the most popular exhibition in that German exhibition some 15 years back. So Malthus's water wheel was demonstrated together with Just next to this there was a computer, and on the computer the solution of the Lorenz equations were shown. So there was a synchronization between what is seen with this water wheel and what is shown on the computer screen. So people were able to appreciate that. Okay, so how something. In fact, many textile industries have used Lorenz's butterflies, okay, as prints on their textile. Okay, so that's of commercial value as well. You can, in fact, if someone is innovative, I would suggest that solving such equations, you can come up with very nice patterns, and there might be a nice way of repeating these patterns on the textiles. It could be a commercial venture also, trying to solve some of these Lorenz type of equations. There are a number of things. Many movies have come. The Butterfly Effect, Jurassic Park also, in a way, I mean, not exactly that. Now let me end the Lorenz's lecture with some deserts. Okay. So Lorenz was known for some sort of uncertainness in the model. Okay, so that was the impression at that time. So when he died at the ripe age old of 91, this should be 91, I'm sorry. Funeral services are scheduled for 7:31 or 5:29 or maybe 9:57. Okay, so that was one of the, deliberate things. The father of chaos theory, Edward Lorenz, died at age 91. The theory says that a small effect can cause major changes. He came up with the idea after making a mistake on his tax return. So that was deliberately put in one of the newspapers. See, what he titled one, yes, this is very important. He titled this, one of his lectures, to make it very interesting, at the Royal Society, he titled his lecture as follows. If the flap of a butterfly in Brazil, okay, the flap of a butterfly in Brazil can induce tornadoes in Texas, USA. What are the states? You have Brazil, that is South America. You have North America, and some little change in one place can, that is, signal, one can have that in North America. It's a repercussion in North America. That's what he titled his lecture, to make it more attractive. Okay? Because, what was the reason? If you start with some initial solution, it could just go anywhere. Okay, so that was the reason. So now, next one. The theory says, Lorenz's theory says, air movement created by a butterfly could eventually work up into a hurricane. So, Bush was told about Edward Lorenz and his work. This is just a joke. Okay, Bush would not understand anyway. Ever since hearing that, President Bush has sworn to hunt down the butterfly. Okay, that was a joke, but he did not feel that. Edward Lorenz died. Doctors say the cause of death was cancer, while others theorize he was blown out of his hospital bed by a butterfly flapping its wings in Indonesia. Okay, so that was a tribute to the type of work that he did. A couple of years ago, the spirit of Lorenz, Ed took us up Welsh Mountain to a cave, gave a lecture on chaos theory. One of his students says in admiration. He was in his late 80s at that time. Mind you, till the last week of his death, he wrote a paper. Till the last week of his death. Okay, that was the spirit he carried. This is, I'll just skip that. Many books. These are only some of the books I have just shown it here. Many books have been written on the Lorenz equations. There are a lot of publications in communication, in, as I said, stock market, financial analysis, many other things. Okay, there are a lot of publications of this. If someone wants this, one can take a copy of the slides. Let me say this. He had the opportunity to live a full life and died among loved ones. Aside from mathematics and weather, he also had a passion for hiking. passion for writing. That's the photo I have chosen to include here. This is available on MIT website. A student talks about it. Lorenz out in the field, smiling in his element, air blown around by the very wind he was trying to predict. Okay. So the butterfly flew away in 2008. That is what someone wrote. They flew away from Earth. Such was the craze for Lorenz model. When I was in London, on the London tube, on the train that is, I was surprised to see this particular poster. Okay, this poster was shown. That was to popularize mathematics. Okay, to make people furious about that. It has found itself on even mouse pads, and that is the fascination, on mugs and many things. You can, for example, have National Degree College there and say, I love maths on the bags. Go green can be another thing which you say from this particular thing. So you can do a number of things. One thing I realized from what I read about Lorenz was, only when you are innovative, only when you are passionate about what you are doing, will you get noticed. Okay? You don't do work to get noticed, but you eventually get noticed. Okay? So, you see this picture here. Again, Greg Lorenz. Okay? So, seeing that he was Edward Lorenz, a pioneer in whatever he did, and this Greg Lorenz, a painter, I told one of my friends, I am tempted to change my name to Pradeep Lorenz so that I become famous. So this painter, Lorenz again, so if he had shown if he had shown two photographs, no one would have noticed. So he showed this in a painting exhibition and called it Painting the Sky. Many people came and saw. It was Morphin basically. Who's that? Yes. So he is, in contrast to Edward Lorenz, in contrast, that's what I am saying, he is what a teacher should not be like. Okay? So that is Bowman learning for you. Now, even these people are important because you know that someone should not be like him. That is also important. So that is 3 idiots for you. Chase excellence, success will follow. You need not chase excellence in fact. Yeah, if you chase excellence, success will follow. You need not chase success in fact. I will end up very soon, okay? Now this is something which is very motivating. This is called as the Ice Princess. This was a movie which came up some years back. In 2005. The princess, when we say princess, they are not able to do what the subjects are capable of doing. When the ordinary people are capable of doing, the princess cannot do, for example, generally. The princess said, okay, let me learn skating, ice skating, and compete. So she starts skating, but she does not know how to skate, so she keeps falling. Then what she does is, in B.Ed, when people do the B.Ed program, they have what is called as micro-teaching. This is something very similar to that. When we talk about soft skills, these things are very, very important. One can use this in our own teaching methods. So take this. So what did the princess do? She took a video of what she had to learn. She programmed the move that she desired to learn. She practiced with the help of what she figured out through her programming. Finally, she gave her performance and won the competition. That is very important. That earnestness, that desire, that passion to do things was there in the princess. She wanted to do it. That is what made her succeed ultimately, even though she was a royal. What is this? Great Wall of China. But there is a message this conveys. You might go however high you can, but there is a long way to go horizontally. Okay, that is what it conveys. You might go however high you can, but there is a lot to go. I mean, there is a long way to go horizontally. I managed to climb up to the Great Wall of China with great effort, and that is what it is. Thank you very much.